Minimum spanning tree. A minimum spanning tree or minimum weight spanning tree is a subset of the edges of a connected edge-weighted undirected graph that connects all the vertices together without any cycles and with the minimal possible total edge weight. That is, its spanning tree, the sum of edge weights, is as small as possible. More generally, any edge-weighted undirected graph has a minimum spanning forest, which is a union of the minimum spanning trees for its connected components. There are quite a few cases of minimum spanning trees. One example would be a telecommunication company trying to lay cable in a new neighborhood. If it's concerned to bury the cable only along certain paths, when there would be a graph containing the points connected to those paths. Some of the paths might be more expensive because they are longer or require the cable to be buried deeper. These paths would be represented by edge with larger weights. Currently, it's an acceptable unit for edge weight. There is no requirement for edge length to obey normal rules of geometry such as triangle equality. Let's say something about spanning trees. A spanning tree for that graph would be a subset of those paths that has no cycles but still connects every house. There might be several spanning trees possible. A minimum spanning tree would be one of the lowest total cost, representing the least expensive path for laying the cable. To solve any various problems on these topics, we used exactly four algorithms. Prim's and Kruskal's algorithms are most popular, but we will crash about them a bit later. Okay, now I will say something about our classical algorithms. The first algorithms for finding a minimum spanning trees was developed by Czech scientist Otakar Borůvka in 1926. Borůvka's algorithms takes OM log n time. A second algorithm is Prim's algorithm, which was invented by Wojciech Jarnik in 1930. And its right time is either O m log n or m plus n log n, depending on the data structures used. The third algorithm commonly in use is Kruskal's algorithm, which also takes O m log n time. Fourth algorithm, not as commonly used, is the reverse delete algorithm, which is the reverse of Kruskal's algorithms. Its runtime is O m log n or log n in cube. All these four are greedy algorithms. Since they are in polynomial time, their problem of finding such trees is in FP, and related decision problems such as determining whether a particular age in the MST or determining if the minimum total weight exceeds a certain value are in P. Okay, let's see the presentation of Kruskal's algorithm. The idea is very simple. We are going to take the edges and we are going to sort them by weight. And we are going to consider them in order of ascending weight. And the algorithm is simply add the next edge to the tree, unless that edge would create a cycle. If the edge creates a cycle, ignore it and go on to the next one. Let's look at demo of Kruskal's algorithm. Okay, we have the edges sorted by weight and we are going to take them in ascending order of weight. You can see it here. For example, D is 5, then BD is 6 on ascending order. Let's start. At first we are taking DE because it's the smallest one. Then we take BD FE. The next smallest is AF. Let's check the next smallest, BF. We're not taking them, we're skipping it because of BF makes a cycle. You can see it here. So we just skip it. Let's see next one, CF. CF doesn't make a cycle, and it's the last edge we must take. If we will see on AC, it also makes cycle and we need just to ignore it. Next one, CD, creates a cycle, and we can just keep going and see that the other edge in the graph creates a cycle. And when we're done considering all the edges, then we have computed the minimum spanning tree. That's with Kruskal algorithm. Let's see the Java implementation of Kruskal algorithm. At first part, we just built simple priority queue. Then we use union find for checking cycles in our graph. Let's see the main loop of our algorithm, which is white. We have got an edge in the priority queue, and we want to take the smallest one. We want to get its vertices V and W, either and other. And then we want to check using the union find algorithm if they are connected. Also, if they are connected, we don't want to do anything. If they are not connected, then we want to merge them and put that edge into the MST. That's it. And then that's the full implementation, and then we have the edges method for the client to return the minimum spanning tree. It's quite a compact implementation of a classic algorithm. Okay, let's see the presentation of Prim's algorithm. It's just how to get the mean weight edge that connects to the tree. And this is a more efficient way to do it. So again, we start out with our graph, started from A, and let's get going. So now the priority queue vertices, and so there are 3 vertices that are just one edge away from the tree. You can see it on demo. And we keep them on the priority queue in order of their distance to the tree. We need to choose the smallest one, here it's the 8, AF. Let's keep going. Here we have 4 vertices from F. There are BF, CF, ZF and EF. Also we need to choose the smallest one. There it's 7. We choose it and get going. So the 7th is the smallest thing in the priority queue. And so we put that on the MST. And now we'll look at everybody connected to 1. And again we need to choose the smallest one. Here it's 5, DE. We're going again. BD, it's 6. And on this moment, in between the vertices would be the edge BC with the highest value, then we would choose 11 CF, and this would be an example of decreasing K. But on this example we do not have such an edge, therefore we just choose the smallest one, so it's 11 CF. Okay, again it's the easy version of Prim's algorithm. It's an implementation that always connects to the tree, the vertex that's closest to the tree. That's all. Now we want to show you an example of solving the problem on minimum spanning tree using the Prim's algorithm.
The task is telling us that in a material region there are n small cities, but there are no roads that are connecting them. And Akim of the region decided to correct the situation and connect some cities so that along these roads one could get from any city to any other city. But unfortunately, the state budget is very small, and Akim decides to save money by reducing the total length of all roads built. So that's, I think, makes sense that we're gonna use the MST algorithms and to connect all the points on XY plane with. So the input file format tells us that the first line of the input line contains the natural number n, the number of cities, and the next n lines contain x and y coordinates for any ice city. So the output should be like the showing us the length of all roads that are connecting them. So the tasks is telling us that we have like n cities on XY plane, and we got the information about where every city is pointed. Like in this example, we have 6 cities. The first city is located on the X1 and Y1. The second city is located on X7 and Y1. So, and so on. The output shows us like the lengths of all lines that are connecting the points. So that's what we should get. So grading policy for using the most efficient time complex MST algorithm and passing example test is 50 points, and passing the other 5 tests that doesn't include this example test is other 50 points. So overall we got like the 100 points. So in this example, in this grading policy, we have like saying that we need to understand what MST algorithms is most efficient in time complexity to solve this problem. So to solve this problem, we gotta like get all the points on XY plane, and any point can be connected to other point. So we are just making roads. So we're deciding from which city to where we can just connect road, and it will be like the sum of the lengths of the lines will be like minimum. So if we are gonna like understand how many vertices we have and edges, we have like edges like sum from 1 to v. Okay, so from one city we can go to another n minus 1 cities. So the second city we can go from from this city to n minus 2 cities. Why? Because like from first to second we are already connecting, so the sum of the all edges are like the sum of the integers from 1 to n. So that's the that's the problem. We have like enormous an amount of the edges, so we need to like minimize the time complexity. And if you watched like the previous stage of this video, it's explained that the Prim's algorithm are using like a number of vertices multiplied by log e. So that's the point of this task. So we're just gonna use this premium MST class in our main Java class. So let's add the let's add the static main method. I think we will need like the only scanner for scanning the first integer and scanning other and multiply by 2 integers. So scanner in new scanner. So we done it. So next thing, we're gonna just get the values of these integers. Like first integer will be like v. Int v will be like in next int. Next thing. So first of all, let's just create our own class for points. Like we got a point on XY plane, so the point class will just help the X and Y integers. So let's create a new Java class, name it points. So here we will have double X, double Y, and the point constructor, we're gonna give the X and Y. This X will be equal to X, this Y will be equal to Y. So the next thing, we're gonna just generate the getters for these two parameters, X and Y. So that's pretty much it for the point class. We're just gonna get the X and Y's and methods for getting X and getting Y. So we're setting X and setting Y by just creating the point object. So let's create the points array with v points. Like I mentioned before, we have like the vertex numbers and the vertex coordinates. So we'll go through v, and we will initialize every element in points array. Points I equal to new points. So to create the points on i's index, we need like x and y coordinates. So we're gonna get x and y's coordinates by the scanner. So that's what we're just reading through. So now we're gonna go through and let's first add the edge-weighted graph. So in order to use the premium MST, we need like just edge-weighted graph. So that's it. So name it graph, new edge-weighted graph, v vertices, So we initialize the graph. Now we need to add like the edges. So as I mentioned before, in for example, from how many edges we have like the sum of the from 1 to v, all of the integers, because we can build from one point to other points, like any amount of the edges. So that's we just need to get all the options of distances from point 1 to point 2, for example. So we're gonna go through first 4, we'll go through the v, and the second 4 will go through the from 0 to I. So the point is, we're just gonna not from 0 I plus 1 to v. So that's gonna be clear, I think. If you have like, for example, let me show you this kind of example. Have like 1, 2, 3, 4, 5. We can get from 1 to 2, from 1 to 3, 1 to 4, 1 to 5. And from the second vertex, we can go through the 3, go through 3, second 4, second to 5th. So that's pretty much showing us how like for I and J works. So let me just delete this. So we have like the points array that have been initialized, and we can get the X and Y attributes for every point that we have. So we will need to calculate the distance from i's to j's points every time. So we're just gonna create the distance of type double and write like math. If you remember, like to find the distance from point A to point B is like the simple formula like this: math qrt that will have math pow of points I get x minus points j get y, and to the power of 2, plus another math pow of points get points I get y minus points j get y, and to the power of 2. So this formula just gonna calculate the distance from point I to point j. We're gonna add edge E, new edge with I and j, and the distance from I to j and j to I. So we're just gonna add the E to our graph. Add edge E. So Now we have like the all combination of the edges that can be in our graph, and now we need to implement the MST algorithm. So we're just gonna write the prim MST, MST, and new prim MST, and we're gonna give this MST the graph object that we have built through this for loop. So now we're just gonna print the MST's weight. So let's check if everything works well. Like first, we're just collecting the information here, like scanning everything. Then we're creating the graph. Then we're going through the two loops for I and j and calculating the distance by the formula of square roots and power of points I get x and point j. So oops. Here we have the problem get x, so that should be get x, and point I get y minus point j get y. So everything to the power of 2 and summing them. So let's run. So let's run this test code. So I think the answers are the same, like 9.6568. So 9.6568. So that's pretty much it. Everything, I hope everything's clear. So to be honest, like the task is not so difficult, and the MST topic also is not so difficult to understand. It's like the simple things. So hope you like this video. I wish you good luck in just make in learning the algorithms further. Goodbye.